going to start where Jörg finished. So I'm going to start by defining mixed subdivisions. And actually, the first thing I have to do is correct Jörg. I've corrected myself a lot of times during these 2 weeks. Now, for a change, I'm going to correct someone else. So this is not exactly what mixed subdivisions are. Rather, if you call n the cardinality of P, and, well, I guess I should write it over, but let me leave there so that we can compare. First of all, instead of speaking of polytopes P and Q, let's be more general and let's speak about point sets, A1 and A2. And let me call n, or n1, the number of points in A1, and n2, the number of points in A2. We know there's this natural projection from the simplex with n vertices onto A1, the projection that just sends each vertex to the corresponding point of A. And there's a projection between this other simplex and A2. And now what we are going to do is we are going to cross those projections. This gives a projection between this product, and in principle you would say this product here, but then I can compose this with the projection from the product to the sum. Okay? So I have this. This is my projection now. Okay, this is going to be my projection. And, well, the vertices here will consist of one vertex of this thing and one vertex of that thing. They will have two components, one being a vertex there and one being a vertex there. And this map is the map that sends E1, let's say A, E sub I1, comma, E sub I2, where E are the vertices of this thing, onto the point A1 plus A2. Let me write it this way. So A1 will consist of points A1, 1, comma, A2, 1 up to AN 1, and A2 will consist of A1, 2 up to AM 2. Okay? I could use A and B, but the thing is a bit more symmetric if you do it this way. And actually, instead of doing this with two A's, I can do it with K A's. Okay, so I can always, starting with K subsets of RD, and I mean, having all my subsets in the same space is important if I want to add them. Starting with any number of subsets, point sets in RD, I can build this projection from the product of simplices, one simplex for each point set with as many vertices as this point set has points. And I build this projection from this product onto this Minkowski sum. And this is the projection I'm going to be interested in. This is the projection that I'm going to call pi sub m. And our first definition of mixed subdivision of this family of point sets is that it is a pi sub m induced subdivision of this sum. So it's always going to be a polyhedral subdivision of this point set, polyhedral subdivision in the sense of my first lecture on Monday last week. But also, all its cells have to be images of faces of this big polytope. Okay, that's what pi m induced means. And for example, here we see why it is important to allow repeated points in a point set. Because what happens if my point sets are equal to one another? Then the Minkowski sum has n times m element, except they will all or almost all come in pairs. If I pick a point A in A1 and a point B in A2, I want this to be a point in the Minkowski sum, and I want to consider it as a different point as if I take A in A2 and B in A1. Okay, for example, if I'm going to add this point set with this point set, then I will have this point set with a repeated point there. Okay. And I want my subdivisions to be subdivisions of this thing with this tricky definition that I have when in case of repeated points. Okay, so this is the end of page 1, the fiber polytope perspective of what a mixed subdivision is. But this perspective doesn't say much, especially if you're not familiar with fiber polytopes, and you're not familiar with fiber polytopes because you've seen them for the first time this morning. So let's go to a more down-to-earth definition. And first, I'm going to define. So actually, the only thing I need to define is what has a cell here, a set of points here, a subset of points here. What needs it to satisfy in order to be the image of a face there? And that's actually very easy. What are the faces of this product? Faces in a product of polytopes are just products of faces of the different factors. If you take a prism, which is a triangle times a segment, this bottom face is the triangle itself, which is a face, cross the bottom point of this segment. The other one is the triangle cross the top point of this segment, and these are faces. Bottom point, top point are faces. These ones are the product of this segment in the triangle and the whole segment here, which is also a face, and so on and so on. So the mixed, the cells that I am allowed to use in a mixed subdivision here are the ones which are projections of products of faces of the simplexes. Now, everything is a face of a simplex. So the things I'm allowed to take are all obtained as follows. I take a subset of A1, a subset of A2, a subset of A3, and so on, and the Minkowski sum of them will be a valid cell. Okay, so let's write this definition. A subset of A1 plus AK is called, and remember that this is a set of points with maybe repeated points, is called a Minkowski cell. If it can be decomposed or written as B1 plus BK for certain subsets BI contained in AI. And then what is a mixed subdivision? A mixed subdivision is a polyhedral subdivision whose cells are all mixed Minkowski cells. Let's do an example. Let's consider A1 equal these three vertices, and A2 equal these three vertices. Let me give labels to them. This is going to be A1, A2, A3. And now, for simplicity, I will use B's. This is going to be B1, B2, and B3. And then what's a mixed subdivision? Well, first of all, it's a polyhedral subdivision of this set of 8 points. I will have a repetition there because, as it turns out, yeah, it's actually 3 points here. Yeah. 3 times 3 is 9. I have 3 points there, and I can tell you what they are. So, for example, what is this point here? This point here is going to be the sum of this and this, A2 and B1. This one here is the sum of A3 and B1. And now I can go on, because this is going to be A3 plus B2. This one is going to be A1 plus B2. This one is going to be A1 plus B3. And this one is going to be, I guess, A2 plus B3. There's something close to flips here, right? I'm changing 1 point at a time. And these are going to be A1 plus A1, plus B1, A2 plus B2, and A3 plus B3. And they all coincide. For example, if you take your origin here, then A2 equals minus B2, and then A2 plus B2 equals 0, and this happens for A1 plus B1 and for A3 plus B3 also. So I have these 9 points, and I want to construct all the polyhedral subdivisions of that. First, the trivial subdivision is a mixed subdivision. Because this point set here is the sum of a subset of A1 and a subset of A2. It's just A1 plus A2. So that's a mixed subdivision. But there are others. And there are actually not that many. There are actually 7. You have this picture in the notes. So I will not write everything in, but let me just say that in order to specify a mixed subdivision, this picture is not enough. I have to tell you how to write this as a sum of something in A1 and something in A2, and how to write this as something in A1 and something in A2. And let's do it at least for this one. This one is A1, A2 plus B1, B2, B3. So this cell consists of 6 points. This cell consists of six points, 1, 2, 3, 4, 5, and 6. These 2 points are A1 plus B1 and A2 plus B2. I mean, this is an abbreviation of this, right? So it's the sum of these 2 plus these 3. This gives me 6 points. And this is A1 plus B1, and the other guy is A2 plus B2. And here, this is going to be A1, A2, A3 plus B1, B2. And why is this a subdivision in the first place? So it's clear that these 2 are Minkowski cells. But is it clear that this is a mixed subdivision, that this is a subdivision? Well, we have to check this property, this good intersection property. And we have to check that this phase, we have to check that this as a phase of that is the same as this as a phase of that, which is not obvious. But it's not obvious but true. What is this phase in here? Well, it's, I guess, so you have to take this segment and everything which is in that direction, but this segment is perpendicular to that direction, so the whole thing is there, A1, A2, and then B1, B2 here. So this here is A1, A2 plus B1, B2. This, as a phase of this point set, consists of 4 points, A1 plus B1, A1 plus B2, A2 plus B1, and A2 plus B2. And you play the same trick here. You go into that direction, and then here you get A1, A2, and here you get B1, B2, because this is perpendicular to your direction. So, yes, these two phases intersect properly with these labelings, and this is a mixed subdivision with these labelings. And you can do the same in the other 6, in the other 5 things. And this is actually the set of all mixed subdivisions of this point set, and this is a poset. There's refinement. They are subdivisions, and we have defined refinement for subdivisions. So this must be a poset. And what poset is it? Do you recognize it as a poset of faces of some polytope? Yes, it's the poset of faces of a triangle. The triangle itself, the 3 edges, and the 3 vertices. Okay? Because the fiber polytope of this projection is a triangle, and all the pi m induced subdivisions in this example are coherent, so they form the poset, the phase poset of this secondary polytope, fiber polytope. Now, what is the analog of triangulations? We have the analog of subdivisions. What is the analog of triangulations? Well, the things in the bottom. And how can we characterize them? We can abstractly say that they are the minimal elements in the poset of mixed subdivisions, but we can also give another characterization of them. A Minkowski cell is fine. Fine meaning there's minimal if 2 things happen. So what do I need in my Minkowski cell to be minimal? One thing I need is I need each of these summands to be a simplex. A Minkowski cell B1 plus BK is fine if B1 up to BK are finely independent sets. I mean, each of them is an affinely independent set. Okay, each of them is an affinely independent set. And the second condition I want, in this example that we have there, this plus this is not a fine cell. There are things which are finer than it. This consists of 6 points, and I can still refine this. I can refine this in 2 ways actually, either like that or like that. And why is it the case that I can refine it? Well, the reason is that this affine space and this affine space have a common intersection. I mean, if you put them together, they have common directions. Okay, so the second condition I want is that B1, the affine spans of B1 up to BK are, where am I? Are transversal to one another, if you want to say it like that, or they are complementary affine subspaces. Meaning that the dimension of B1 plus the dimension of BK equals the dimension of the sum. So that's one way of saying it. There are different ways of saying it. Okay? And this is not the case here. The sum has dimension 2, and this has dimension 1 plus 2, which is 3. So, which means what are the possibilities if I'm in dimension 2? What are the possibilities for fine cells? I can have two types of fine cells. I can have a triangle plus a point, plus a point, plus a point, plus a point, and so on. Or I can have a segment plus another segment plus a point, plus a point, plus a point, plus a point. And, of course, I need these two segments to be non-parallel. So in particular, if we're in the plane, and during most of this talk we are going to be in the plane, if we are in the plane, the Minkowski cells that I am allowed in fine mixed subdivisions are going to be triangles or parallelograms. Okay, I haven't defined fine mixed subdivision, but of course, a mixed subdivision is called fine if all its cells are fine Minkowski cells. And this is equivalent to saying that this is a minimal element in the poset of mixed subdivisions. Okay. And they are the analog of triangulations in the mixed world. So that's the end of part 1 of the talk. Let's go to the Cayley trick. So I'm now going to define something called the Cayley embedding. And, well, the Cayley embedding of A1 up to AK is the point set that I will denote C for Cayley of A1 up to AK, defined as, and this is maybe not easy to understand at first sight, but it's not that difficult either. This thing, where E1 up to EK are an affine basis for R to the K minus 1. Which means this thing lies in R to the D times R to the K minus 1. Okay. This lies in R to the D times R to the K minus 1, these two, and these two, and these two, and so on. Okay. What's the idea behind this? Well, the idea is you are going to take a simplex in R to the K minus 1, and then on top of the first vertex, you are going to put your first point set. On top of the second vertex, you are going to put your second point set, and so on and so on. So here you would put A1, here you would put A2, and here you would put A3. And this lies in an orthogonal space to this. Okay, so that in the end, you have something which lies in Rd times Rk minus 1. Two examples. What if k equals 2? If k equals 2, what you have is your point set A1 in a hyperplane and your point set A2 in a parallel hyperplane. Okay? You'll have A1 line in a hyperplane, and you'll have A2 in another hyperplane, and then you'll consider this point set contained in R to the d plus 1. For example, a cube. A three-dimensional cube is the Cayley embedding of two squares, or it's the Cayley embedding of two copies of the same square, in a sense. And example 2, if you have A1 equals A2 equals AK, what do you have there? It's going to be the product of your point set with the simplex. The simplex of dimension k minus 1. And why is the Cayley trick interesting? Well, the reason is, I want to leave some of George's stuff there because eventually we will come back to some of those things. And the theorem says that the set of polyhedral subdivisions of this Cayley embedding is equal to, or there's a canonical bijection if you prefer, to the set of mixed subdivisions of A1 plus AK. And perhaps let's go to page 11 in the last page in the notes, because I guess that's the nicest example of this bijection. So what is a sonotope? A sonotope is a Minkowski sum of segments. What is a Cayley embedding of segments? Well, you need not know this, but it's a special type of polytope called Lorentz polytope. So people here who know what a Lorentz polytope is may know a different definition, but one definition of Lorentz polytope is a Lorentz polytope is a Cayley embedding of segments. And in particular, the Cayley trick tells me that there's a bijection between the sonotopal tilings of the sonotope, mixed subdivisions of a pi-induced subdivisions of a sonotope are the mixed subdivisions, the sonotopal tilings. So there's a bijection between sonotopal tilings of the sonotope and all the subdivisions of the corresponding Lorentz polytope. This is the theorem you have in the upper half of the page. But let's now look at the simplest example. So we are going to suppose that A1 up to AK are segments, but we are going to suppose that they are the same segment. Then, what is this thing here? It's the segment times a simplex. It's the prism over a simplex. So the theorem is telling me that polyhedral subdivisions of this thing equal, what is this Minkowski sum? I have k copies of the same segment. The Minkowski sum is a segment, k times as long. Okay, so let's call them sonotopal tilings. Let me draw it like this. Now, does this remind you of something? These are monotone paths in the cube, because here I'm considering the projection of delta 1 times delta 1 times delta 1, because all my point sets have two elements. I'm considering the natural projection of that into A plus A, but this is the same as saying the k-dimensional cube, if you want, and this is one dimension, and Georg has told us that when this is one dimension, what we are looking at is monotone paths in this polytope. So this thing here is the same as monotone paths in the k-dimensional cube. No wonder both things are k-factorial, have k-factorial minimal things. Well, monotone paths are only the fine things, so monotone paths are only the minimal elements, so this is not completely true, but it will be true if we put fine here and if we put triangulations here. And no wonder that the secondary polytope of this prism and the monotone path polytope of the cube are the same polytope. They are both permutahedra. Okay? So the Cayley trick explains this strange coincidence of permutahedra as monotone path polytopes for the cube and as secondary polytopes for prisms. Now, what is the proof of the Cayley trick? If you go back to page 5, there is a so-called one-picture proof of the Cayley trick. And let me give you the one-picture proof here first, and then we'll go to this example there. So first thing I need to do is I'm going to draw this segment vertically. Now, how can I make a bijection between these 6 triangulations and these 6 monotone paths? Well, first thing I should do is I'm going to put labels to the 3 directions of the cube. So I'm going to call these 1, 2, and 3. And then a monotone path, as Francis told us the other day, a monotone path in the cube consists just of a permutation of these 3 numbers. You choose an order in order to traverse the different directions. So, for example, 1, 2, 3. Let me do it the other way, actually. 1, 2, 3, for example, would be this monotone path here. Now, we know that these things are in bijection to permutations also, and the bijection is essentially, we call this 1, 2, and 3, and we call this 1 prime, 2 prime, 3 prime, and we started here. We joined this first to point 1, then to point 2, and then to point 3. And my question to you is, how can I make this picture appear here? And the answer is extremely simple. Is you just intersect with this line. And then along this line, I'm going to see segments. Each of these segments will correspond to one of these simplex. And actually, the order in which the segment appears is just the order in which I have put the simplices. So if I label my simplices 1, 2, 3 according to the order in which they appear, I will have these 1, 2, 3 there. And actually, there's an even nicer way of thinking about this. Remember that all that is behind this is that that thing is the Cayley embedding of K equals segments. So what I'm going to do is I'm going to label these segments. This is going to be segment 1, segment 2, and segment 3. And now what happens here is that every simplex will consist of one of these segments and then 1 point of each of the other. And the simplex, if this is segment 2, the simplex will naturally be labeled 2. And what I see here is the trace, in a sense, of simplex 2. So this proves the Cayley trick in this particular case. And the general proof is actually exactly the same. You have an example here. I have the Cayley embedding of a square and a triangle. I have a certain polyhedral subdivision of it consisting of 4 cells. And my claim is that if I take the middle intermediate plane between the plane of the square and the plane of the triangle, what I see there is a mixed subdivision of the Minkowski sum, a scaled Minkowski sum of the square and the triangle. Okay, so this bijection is just the following. You have your Cayley embedding here with A1 there, A2 there, A3 there. Then, if you cut this with the middle fiber, the barycenter fiber, the fiber over the barycenter of this simplex, here, what you have is the average, or if you want, the scaled Minkowski sum of these 3 point sets. And my claim is that every subdivision of this thing here will appear here as a mixed subdivision, and vice versa. Every mixed subdivision there can be extended to a polyhedral subdivision of the whole thing. And because this bijection is so simple, it certainly will preserve, for example, coherence. Coherent in the world of subdivisions is what we have been calling regular during this course. And what this says is that regular subdivisions will correspond to coherent mixed subdivisions. Coherent in the sense of pi m coherent, coherent with respect to this projection. Minimal things here, which are triangulations, will correspond to minimal things here, which are fine mixed subdivisions. And certainly bistellar flips here. This is not written in the notes, will correspond to the natural notion of flip here, which Joe hasn't spoken about, and I'm not going to speak about, but there's a natural notion of flip in the world of pi-induced subdivisions. Let's call these pi m flips, whatever they are. So this is the end of the second part of this talk. And now we're going to see two applications of the Cayley trick, two applications that I like a lot. One is triangulations of cubes. And actually, we're going to see three applications because triangulations of cubes will appear in two ways. Two are triangulations of cubes, and the third is triangulations of the product of simplices. Now, the three-dimensional cube is just the Cayley embedding of two two-dimensional cubes. And what this means is that I can picture triangulations of this thing as mixed subdivisions of this thing. Okay, and let me draw. I'll need like 8 of these things. Now, what is a mixed subdivision? Well, I've told you there somewhere that in the plane, a mixed subdivision is going to be a subdivision into triangles and parallelograms. The triangles have to be triangles contained in one of these two things. And there are not that many, right? I will have either one of these two triangles or one of these two triangles. And the parallelograms need also to have edges contained either here or there. And there are essentially three types of them. This, and then that. This is what I get if I take this diagonal in one of the squares and this diagonal in the other. So these are these 1, 2, 3, 4, 5, 6, 7 things are my bricks in order to build mixed subdivisions there. Let's start building some. And there's one funny thing. Well, I'm not sure why it's funny. There's one interesting thing here. Of course, this is going to be triangulated, and this is going to be triangulated. And these two things will appear there as triangles. The tetrahedra containing these two triangles will appear here as triangles. The tetrahedra containing these two triangles will appear here as triangles. And all the other tetrahedra will appear as quadrilaterals, because all the other tetrahedra in this triangulation are going to have 2 points here and 2 points there. So I need to use exactly 4 triangles, and then the rest has to be filled with quadrilaterals. Now, with these two triangles, I'm going to cover half of the area of that. And each of these two quadrilaterals will cover a quarter of the area, 1/4 of the area, while this one has twice as much area, which means that if I only use these things, I will have 6 cells, 6 tetrahedra in my triangulation. But if I use this one, I will have 5 tetrahedra in my triangulation. And this explains why the cube can be triangulated with 5 tetrahedra and 6 tetrahedra. And actually, there's only one way of triangulating it with 5 tetrahedra, which is that one. That's the only triangulation of the cube with 5 tetrahedra. Well, there's actually 2 of them, because now I have to tell you whether this belongs here or there, and there are 2 ways of saying that. Okay? So this is going to be one of them, and if I interchange the labels, I will have the other one. In principle, I would need to give you more than this, okay? I would need to give you explicitly how this is written as the sum of a triangle here and a point there. But my claim is that if I give you this, the rest is determined by that, because this triangle has to be the triangle in this corner, and this vertex has to be the vertex in this corner. Otherwise, I will not get that in that position. Anyway. So that's one triangulation. That's actually 2 triangulations. Now let's do a flip. And a flip is I'm going to take this triangle, and I'm going to slide it this way. And what I get is this thing here. So that's another triangulation. It has 6 tetrahedra. And this is actually 8 triangulations, modulo the symmetries of this square. because I can interchange the labels. This gives me 2, and I can rotate the square. This gives me 4. 2 times 4 equals 8. And so on and so on. I can construct a full list of triangulations. I can construct a full list of mixed subdivisions of this thing. You have it here. There are 9 types of them. There are 9 types of them. The number represented, the number of different triangulations represented by each of them is written there. And certainly, the sum of all these numbers is 74, which I think, Francis, is the number of triangulations of the 3-dimensional cube, right? So this picture, this is the 74 triangulations of the 3-dimensional cube. Now, I have 9 things here, and there are only 6 isomorphic classes of triangulations of the cube. This is because I've broken the symmetry of the cube partially when I've chosen these 2 parallel faces, right? And if you want an exercise, you have to match these 9 figures into 6 isomorphic classes of triangulations of the cube. Okay? But beware, not all that looks like a mixed subdivision is a mixed subdivision. Well, this actually, does it look? Yeah. This looks like a mixed subdivision. It consists of 4 squares, 4 triangles, and the rest is pieces like that. And this looks like a mixed subdivision. It consists of 4 triangles, and the rest is pieces like that. And I claim that these are not mixed subdivisions. Can anybody give me a proof of that? Well, these 2 things cannot intersect properly as mixed cells, because either I label them 1 and 1, but then this is the upper half of a square, and this is so this is the upper half of a square, and this is the lower half of the same square. Or I label it 1 and 2, but then this is a segment in one of the squares, and this is a segment in the other square. So this as a face of this is not the same as this as a face of that. Okay? And we have the same thing there, essentially. And the rule is that once I've labeled this as 1 and 2, or 1 and 2, every quadrilateral will have its segments, its sides, labeled as 1s and 2s. And all the 1s and all the 2s need to match up. Okay? So, for example, maybe what about this one? This is the one in the top right of your notes. Sorry, bottom right corner of your notes. This square will have 1 and 1 here. Sorry, 2 and 2 there, 1 and 1 there. 2 and 2 there, and 1 and 1 there, so there's no problem. This is a mixed subdivision, and so on and so on. So what's the other application of these 2 triangulations of the cube? Well, Francis told us about triangulating the cube with few simplices. Triangulating the cube with many simplices is easy. You can triangulate it with n factorial and no more than n factorial. The difficult thing is triangulate it with few simplices. One thing you can do is sort of divide and conquer. Suppose that you know how to triangulate this efficiently. If you know how to triangulate that efficiently, and you know how to triangulate this efficiently, then you know how to triangulate this efficiently, essentially. Why? Because, well, let me be more precise. If I have a triangulation of this and a triangulation of that, then I have a triangulation of that too. Because I can divide k plus 2 into, so I can divide ak plus 2, which equals, sorry, ik plus 2, which equals ik times I2, I can first triangulate that. And I will divide this into copies of delta k times I2 into not many copies of delta k times I2 if I have not too many simplices in this triangulation. And now if I know how to subdivide each of these things efficiently, I will end up with an efficient triangulation of ik plus 2. And simple as it looks like, this is essentially the idea behind the most efficient triangulations of Qs that are known so far. And the idea is that, of course, this, you can picture it, triangulations of this, you can picture it as mixed subdivisions of k plus 1 copies of I2. My k is shifted 1 with respect to the nodes, right? I have a k minus 1 there and k copies of the square. I have a k here, and then I need k plus 1 copies of the square. And the best way of triangulating this polytope turns out to be something like that. It's essentially the same idea you have here. You want to use many of these things, and the way to do it is something like that. This allows you to triangulate this thing with more or less 3k squared over 4 simplices. While if you do unimodular triangulations, for example, if you do the standard triangulation of the cube, but in this same thing, you will have like k squared simplices. Now, this doesn't look like a lot of improvement, right? This is only a factor of 0.75. But now you are going to do this recursively. You start with the cube of dimension 3, you apply this, you triangulate the cube of dimension 5, you apply this, you triangulate the cube of dimension 7, and so on and so on. And every time, you are going to multiply your number of simplices essentially by that number, where k is the dimension where you are at a certain step. So essentially, if you do this, what you are going to have in the end is 3, 4 to the n over 4, because you are doing this n over 4 times if you want to arrive to dimension n. And then here you will have essentially the n factorial. This k squared times k plus 2 squared times k plus 4 squared times k plus 6 squared is essentially the factorial, right? And this is 0.866 to the n times n factorial. And if you compare this to the most efficient triangulation of the cube known 3 years ago, or 5 years ago, which was Hyman's. This was mentioned by Francis. Hyman was able to triangulate the cube with this number of simplices. Now we have this number of simplices, which is a bit more, but this is very simple. We can complicate it a bit. We can use, for example, the 3-dimensional cube here instead of the 2-dimensional one. And if you use a 3-dimensional cube and do some computations in order to compute the minimum triangulation of that, then you get this number here, 0.816, which is actually the best way of triangulating the cube known so far. So this involves some computations, but this involves much, much less computations than, for example, the method that Hughes and Anderson used to find the minimum triangulation of the 7th cube. And I have to say that this number here is based on that computations of Hughes and Anderson. So in a sense, this number or this number involves much less computations than this one. And now we've come to the last application of the Cayley trick. Well, the last application of the Cayley trick I want to speak about today. because of course one can find others. And it is triangulations of delta 2 times delta k, which of course is the Cayley embedding of k plus 1 copies of this triangle. So I have to triangulate this big triangle there. Suppose that k equals 8. And the first question is, what are my fine mixed cells? They have to be either triangles, but triangles contained in one of these things. So they have either to be triangles like this, or sums of segments, but segments contained in these things. And there are three possibilities. I can have this, I can have that, and I can have that. And now you start filling this in with things like that, and what you get is a mixed subdivision of this thing, and hence it is a triangulation of that thing. And you have an example there. You can draw many, many examples. And here I claim that you actually don't need to care about things intersecting properly. Actually, let's go a bit farther. So this triangle comes with a natural tiling, okay? A natural triangle tiling. Now, I hope everything matches perfectly. Well, it should. You know what I mean, right? There are going to be some upward triangles and some downward triangles. And what does it mean to triangulate this like that? Well, I'm going to match each of these things consists of an upward and a downward triangle. So some of these triangles here are going to be matched to one another, and some of them are going to be alone. But only upward triangles are allowed to be alone. And if you count here, you'll see that you have exactly k more upward triangles than downward triangles, which means that this tiling here will have k of this, and then the rest will be things like that. And if you count, you'll see that you'll have k squared minus 2 divided by 2 of one of these three things. This number in total, of course. And my claim is that if you do that, so at the end you will end up with 8 triangles somewhere. Of course, not all possibilities are allowed, because this is not allowed, but you will end up with 8 triangles somewhere. And my claim is that if you label this from 1 to 8, this will uniquely determine a triangulation, a mixed subdivision of this thing, and in particular a triangulation of that thing. Or in other words, you tile this as you wish using these tiles, and that represents k factorial triangulations of delta 2 times delta k. These tilings are called lozenge tilings. Because these things are called lozenge. And each of these tilings will represent k factorial triangulations of that thing. And for example, here you have the 6, again, the 6 triangulations of that thing. Because this is the Cayley embedding of 3 segments, but it's also the Cayley embedding of 2 triangles. Okay, so here you have, with the labels, you have the 6 triangulations of that thing. And what you have here is actually what you see if you cut your prism along this intermediate plane. Okay. And now with this, you can do many things. You can go further, for example, and draw all the triangulations of delta 2 times delta 2. They are here. There are 5 isomorphic classes of triangulations of delta 2 times delta 2, represented by 5 tilings here. Each tiling will represent 6 triangulations. 3 factorial is 6. But then since you have symmetries, each of my drawings represents more than one triangle, more than one tiling. For example, this one can be rotated in the 3 ways, and this represents 3 tilings and 18 triangulations. This one can only be rotated in 2 ways, so it represents 2 tilings and 12 triangulations, and so on and so on. And these ones on the bottom, they can be rotated. I can triangulate like this, or I can triangulate like that, and this is going to be non-regular. And here I can triangulate as I want, and this is a non-regular triangulation of delta 2 times delta 5. How do you prove that this is non-regular? Well, just prove that this subdivision, as a subdivision of this point set, is non-regular. And that proves that this is non-regular. You can study flips between triangulations, and there are 2 types of flips. One flip is this, and the other, it has a question mark, right? It has a question mark because this is not quite it. So this is a lower dimensional flip, in a sense, because these things are collinear. And since this is lower dimensional, you have to look at the links. And you would say, OK, let's look at the link. Let's look at the next thing here and the next thing there. Well, that's not the problem, or at least that's not all the problem, because suppose that they agree. Suppose that this agrees. If this agrees, then it looks like this is going to be a flip. But unfortunately, this circuit here is the same as this circuit here. Because, well, this is 4 points. This is 4 points. So this represents a quadrilateral in this polytope. This represents a quadrilateral in that polytope, but unfortunately, they are the same quadrilateral, except that I've added different things to it, in a sense. So it means that in order to have a flip, I need to have the same thing here. So I need to have perhaps this, and so on and so on. So for example, let's do an example. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's quickly draw a Lausanne tiling of this thing, and let's look for flips in it, or for some of the flips in it. Oops. You have to be careful. You have to be careful. Okay. So, for example, this is a flip here. This is a flip there. And this is a flip here. And what else? Is this a flip? No, because these go differently, right? Is this a flip? Yes, this is a flip. And so on and so on. And of course, this is a flip, because there's nothing there. And this is a flip, and this is a flip, and so on and so on. And this is a flip, because these go in the same way up to the bottom, and so on and so on. And once you know what flips are, you can try to prove that the graph of flips is connected, and indeed you can. The graph of flips of delta 2 times delta k, the graph of flips between triangulations of delta 2 times delta k is connected. And you can try to derive asymptotic formulas for the number of triangulations, and you have formulas here. The number of triangulations is between the number of triangulations of delta 2 times delta k is between alpha to the k square and beta to the k square for certain values of alpha and beta. And the best values I've been able to compute are written here, but maybe you can improve them, and so on and so on. And this is the end of my talk. And as George said, this is my last talk, and I also want you to know that it has been a pleasure, and it has been a lot of fun being here, speaking and thinking about triangulations for 2 weeks.